we are going to be talking about 7.2. So 7.2, remember in 7.1 we discussed, we just kind of got this introduction of functions of several variables, right? So this is a function of x and y, right? Function of x and y. So of course, right, we're in calculus. So what do we want to do with this function? We want to take derivatives. And remember what a derivative is. A derivative is the rate of change of a function with respect to x. That's what we've been used to so far. We've been used to dy dx being the rate of change of y with respect to the rate of change of x. Okay, so how does y change given a change in x? And it's an instantaneous rate of change. So as you saw in the book, what we found, and you wrote down this definition in your notes, I know you did, because I told you to, right? So the definition, and I'm not going to make this perfect, but I just kind of want to reiterate what this means. So if I have a function f of x, we have something called the partial of f with respect to x. And if you start, so these are weird, right? These like little cursive D's. If you start at the top and come down, they almost look like 2's. This is just, you know, making a suggestion after doing this for a while. So if you start kind of at the bottom and come up, you can kind of make them a little more rounded and make it look kind of like that cursive D that we're going to use to denote a partial derivative. So this right here is the partial derivative. Okay, partial derivative of f with respect to x. So that x on the bottom, this guy right here, tells us that we are deriving this function with respect to x. Okay, so the partial derivative of f with respect to x. In this case, y is treated as a constant. So what I want to look at is if I take the derivative of this function, I want to think about taking the derivative of this function by what would happen if I held y constant, whatever y is, okay, and I looked at what would the change in the function be if I made small changes in x. That's really what this is saying. Likewise, because this is a function of several variables, I have the partial derivative of f with respect to x. I also have the partial derivative of f with respect to y. So same definition, except we have the partial derivative here. I'm getting lazy, so I'm going to abbreviate here, of f, and then in math sometimes we have with respect to quite often in mathematics, so we just use shorthand WRT. So with respect to x, Sarah? Sorry, with respect to y, and in this case x is treated as a constant. So let's do some examples. Treated as a constant, okay? So that's what this means, and I think you'll see that this actually isn't too bad. Now, the second derivatives can be a little tricky, but you guys can handle it. It'll be fine. I'll be there with you. We'll be good. So let's try this other one really quick. Other layer. And let's just do some examples. So, example, find the first partial derivatives of each function. Okay, so let's do a couple, because these are a good time, so we might as well, right? So let's look at this first function here. So f of xy, okay, is going to equal, we'll start off kind of easy, 3x cubed y squared. The other thing you have to do now is we were just integrating, taking antiderivatives. Now we are taking derivatives. So instead of adding and dividing, remember we're multiplying and subtracting. So kind of wrap your head around taking derivatives again. So look at what I'm going to do here to take the partial of f with respect to x. Another way we can write this, and you guys will probably like this better, but another notation that we can write is we say f sub x of xy. So this little x down here, and I don't think your book uses it, which is a little bit weird to me. But this f, if I have this f and the little x as a subscript, you can use that notation as well to denote that this is the partial derivative with respect to x. So again, to take the derivative of this, we're just going to treat y squared as a constant. So what do we do with constants when we take derivatives? Well, let's ignore the y squared for a moment, poor y squared. Let's think about 3x cubed. Okay, what would I do to take the derivative of 3x cubed? Well, remember we leave the 3 I take the derivative of x cubed, which is 3x squared, and that would be my derivative. So the question here is then, what do I do with constants, right, when I'm taking derivatives? Well, the constants just stay and hang out. Hold on. I want to get rid of that yellow really quick because we're going to come back. So again, I have 3. Now I'm going to take the derivative of x cubed, which is 3x squared. And then I'm just going to, again, multiply by the derivative of y, or not, I'm sorry, just multiply by y squared. Y squared is just treated as a constant. Okay, so what is the partial derivative of this function with respect to x? It's 9x squared y squared. Let's look at the partial derivative with respect to y. And you guessed it, another notation for that is just f sub y of xy, okay? So again, I'm going to leave anything that involves an x alone. This is just a constant, so I'm going to just leave that there. I'm going to take the derivative of y squared. I'm going to write that as 2y. I'm not going to leave my answer like this because I know it drives my math teacher crazy. I'm going to simplify and multiply the 3 and the 2. All right, so look at what we have. We have 2 functions now that describe derivatives of a function of several variables. I have how does the function change as x changes? How does the function change as y changes? And we'll look at some examples with actual numbers, which will be a little bit easier. What about something like this? I just want to do quite a few examples so you're feeling comfortable with this. How about 4xy minus x squared plus y cubed? Okay, so the partial with respect to x, right? Let's look at 4xy. So again, the 4 is treated as a constant. The y is treated as a constant. What is the derivative of x with respect to x? That's just 1. So I just get 1 times 4y, which is just 4y. Derivative of x squared is 2x. And then look at this. The derivative of y cubed doesn't have any x's involved in it, right? So the derivative of y cubed is 0. So we're done. Partial of f with respect to y. Same idea here for the top. The derivative of y goes to 1. 4x is treated as a constant, so it's just left with 4x. And then the derivative of x squared is 0 because there are no y's involved. And the derivative of y cubed is 3y squared. So those are my 2 different functions for the partial derivatives of f. Let me create a new slide here. Whoops. Sorry about that. I've been using this a while. All right. So let's look at layer 3. Let's do another one. So same thing, okay? Find the partial derivatives. Whoa, that was a crazy function there. Okay, f of xy equals the square root of 1 minus 2xy squared. Okay, so we got to think about this a little bit, right? Even though I'm taking the derivative with respect to x, I still have to consider my rules that I have for taking derivatives, such as the chain rule. So remember, the chain rule tells us, look at what I have. I have a composition of functions, right? My outside function is to the 1/2. My inside function is 1 minus 2xy squared. So I'm going to bring the 1/2 down. Chain rule says, take the derivative of the outside while leaving the inside. Bring the 1/2 down, take 1 away. Now I'm going to multiply by the derivative of the inside, and this is where it matters that we're deriving with respect to x. So the derivative of 1 is 0. Again, the derivative of x right here is 1. So I just get a negative 2y squared. Don't leave it like this. You need to simplify. You are in Calculus 2. You should be able to simplify this. And then what does that negative do? It goes on the bottom. So I have a negative y squared all over. And you could leave that as to the 1/2, but we started with square roots, so I'm going to go ahead and write my answer in square roots. Okay, I hope that makes sense. So that's the derivative with respect to x. I still, what was this part C? Still have to find the derivative with respect to y, the partial derivative with respect to y. So this stuff is going to be the same, right? Because it's going to be the derivative of the outside. So this is the derivative of the outside. Now, when I multiply by the derivative of the inside, that's where it's going to change, because the derivative of the inside is going to be with respect to y. 0 goes away, So I get a negative 2x times the derivative of y squared, which is 2y. I can cancel one of the 2's. What am I left with in the numerator then? A negative 2xy all over the square root of 1 minus 2xy squared. Good. Let's do one more. Let's do one. So I hope you remember product and quotient rule. Of course you remember the product and quotient rule. So like what if we had something like this? X e to the xy. Okay? So let's do, this is going to be the product rule. Well, for one of them. So let's see what happens here. So the partial of f with respect to x, right? So look at what you have. When I have the partial of x with respect to x, I have a function here, x, that's a function of x, and then I have this e to the xy. That is also a function of x. So you must use the product rule. So remember what the product rule says, first times the derivative of the second. So what's the derivative of e to the xy? We rewrite it, and then we multiply by the derivative of the exponent. The derivative of the exponent is just y. Plus, so I left the first, took the derivative of the second, leave the second, times the derivative of the first. Well, what's the derivative of x with respect to x? That's just 1. And then if you want to, I don't know, you could factor out an e to the xy. That would be kind of pretty, wouldn't it? Yeah, I like that. You wouldn't have to, but I would like you to see moving this y over with the x, right? So I would like to see that. Then finally the partial with respect to y. So now, let's talk about this one. Partial with respect to y. Do I need to do the product rule? I do not need to do the product rule because this guy right here is treated as a constant. So is this. It's like if I had 3e to the 3y. Do you see how I wouldn't have to do that product rule because 3 would not be a function of y. Sometimes if you're unsure as what to do, you can put in a constant for the other variable that you're not taking the derivative with respect to and kind of see what's going on. So I'm just going to leave the x. I treat that as a constant. I'm going to take the derivative of e to the xy. So I'm going to rewrite it, multiply by the derivative of the exponent. The derivative of the exponent is x. So I get x squared e to the xy. That is the partial derivative of f with respect to y. I hope that makes sense. I would like you to look at, in your book, I'm going to save you from me drawing this. I'm not very good at drawing three-dimensionally, but I really want to make sure that you're looking at figure 1 and figure 2 on page 356 because it kind of gives you a geometric interpretation of what these mean, okay? So what this shows you, you know, oh, now I'm just going to do it, Sarah. But I want you to look, oh, wow. This is why. I want you to look at the picture on those pages. Again, page 356. Okay, so the idea here is if they kind of make this like three-dimensional blob looking thing. Okay, so if I have this three-dimensional thing, that this is my f of xy. Okay, so pretend this is a three-dimensional thing. If I look at a specific point, right, that I care about, like let's say I have some point up on this surface right here, okay? And if I think about the derivative of f of x, so this is y, this is x. If I let y stay constant and I let x range, okay? If I let x change, basically what this is saying is that the slope, the partial derivative with respect to x, I'll pretend, is the slope of this line right here. This would be the partial derivative of x, of f with respect to x at some point, you know, a, b. I would plug in an a and a b. Okay, and then the other side of this, I told you I wasn't going to graph this, and now I totally am graphing it. The other side of this is, well, what if we let x stay constant and we let y change, right? If we let y change, if I want the rate of change of y at that specific instant, let me use the same color for this. So if I'm going to let y change, then really what the partial derivative with respect to y is giving me is it's giving me a tangent line in the y direction, okay? So this would be the slope of that tangent line with respect to y at the point AB. So I get two slopes because, again, I'm looking at changing in the x direction and changing in the y direction. So let's go back. We can probably get rid of this. Oh, goodness. It gets so cranky at me. Shouldn't it know what I want it to do? So I just want to do another example, just a couple more examples. I'm going to try and keep this lecture under 30 minutes, hopefully under maybe 25 minutes. So I just, let's do an example here. Let's evaluate you ate, sorry, you know what I mean, whatever. I'm a math teacher. Evaluate the first partial derivatives of f of xy at the point. Okay, so I'm going to give you a specific point now, 1, -3 for the function. And let's just use a function we've kind of already seen. We already took these partial derivatives, so we'll just rewrite this. Minus x squared plus y cubed. So we saw that the first partial derivative of f with respect to x was 4y minus 2x. Now notice that's a function of two variables. So when I evaluate these partial derivatives, I need to have an ordered pair. Before we could evaluate partial, or we could just evaluate derivatives by knowing my x value. But now I need to have an actual ordered pair. So I'm going to take this function, I'm going to evaluate it at 1, -3, just like we know how to evaluate functions of several variables. So I would have 4 times a -3 minus 2 times 1, and that gives me a -12 minus 2, which is a -14. Okay, did I do that correctly? I think I did, right? Yeah, okay, great. All right, so I get a -14. So look at what this, so let me tell you what this means. I'm going to tell you. I'm just going to tell you what this means. So what this -14 means is that if we hold, okay, if we hold x pretty close to 1, right, close to 1, then small changes in x, a small change in x, will result, will result in a -14 times change in f of x, in f of xy. And this means no change in y, right? Y is held constant. Okay, if we hold x close to 1, so I can't go from like 1 to 4, right? That's a pretty big difference. Remember, this is an instantaneous partial derivative, so we want to be close to that point. This derivative will get us good approximations close to that point. But what that says is if we hold x close to 1, then if we slowly move from 1, 1.1, 0.9, pretty close to 1, a small change in x will result in the function changing by a -14 times change in the function. Okay, so it'll be -14 times that we changed. And then likewise, that idea is true also with the partial with respect to y. So the partial with respect to y was 4x plus 3y squared, excuse me. So the partial of f with respect to y at 1, -3 would be 4 plus 3, which is 7. So again, the idea here is if we hold y close to -3, then a small change from -3, right? Maybe a -3.1, maybe a -2.9. A small change in y from -3 will result in a change of 7 times that in the function. Okay, so I hope that makes sense, and that should help you a little bit. If you look at page 357, they have a green box there that they kind of talk about that a little bit more, and they talk about that in more general notation. We might come back to that green box later. I'm not too worried about you knowing that, perfectly or memorizing it for right now. I'm more interested in that you understand how to take these partial derivatives. Okay, so I want to do one more example, and then we'll call it good. So I am going to keep it. I think I'm going to keep it under 30 minutes. You guys should be so proud of me. This is business calculus, so I'm going to do a business. I'm going to do a business example. Oh, look at this thing that we're bringing up. Okay, consider the production function. Love that those rhyme. I am the mother of a 3 and a 5-year-old, so you know rhyming is pretty awesome. Consider the production function. Does that rhyme? I think it does. F of xy equals 60 x to the 3/4 y to the 1/4. We've seen this. We've seen this before, right? This is the Cobb-Douglas production function, where x equals the units of labor that we're going to have, that we're going to spend, and y equals the units of capital. Units, you know what I mean. Capital, okay? So a couple things here. Evaluate. Actually, I don't need a couple things. We'll just do this all at once, okay? So let's evaluate. Why am I having trouble spelling evaluate? I'm going to do some different notation for you here. F sub x of 81, 16 and f sub y of 81, 16. So that's the same thing as saying evaluate the first partial derivatives at 81 and 16, okay? F sub x and f sub y. So I want to evaluate those two. So we need to find f sub x of xy. Remember, we need to take the derivative first, plug in the numbers later. So I'm going to treat the y as a constant. So I'm going to just leave the 60, bring the 3/4 down, take 1 away, right? And then just leave the y to the 1/4 because I don't need to worry about that because it's a constant. It's treated as a constant for the partial derivative with respect to x. Let's simplify that a little bit and we get 15x to the negative 1/4 y to the 1/4. And then let's just, for the fun of it, get f sub y really quick. Oh, and I should have put on here to interpret the results. Interpret the results. Oh. My handwriting just gets worse as the day goes on. And it's kind of late in the day, so. All right, so I'm going to have 60. I'm going to leave these two. They're just constants. Bring the 1/4 down. Take 1 away. Okay, and then I'm going to take 1/4 of 60. Oh, I'm sorry. Up here, this should have been 45. 1/4 of 60 is 15, and 15 times 3 is 45. And then 1/4 of that is just that. So here are my two partial derivatives, okay? So I'm going to plug these numbers in, and I'll go ahead and do that for you. So, well, you are welcome to pause the video and do it yourself. So I have 81 to the negative 1/4 times 16 to the 1/4. Okay, so if I do that, let's see what I get. I already did that. I get 30. Okay, and then f sub y of x. Oh, I'm so sorry. This should have said 81 and 16. I'm sorry about that. Sorry about that. I can erase that. Let me get rid of that really quick. Sorry about that. So I want to make sure, you know, if this is in your notes, that you have it correct. 81 and 16, and here 81. You know, I used to, in graduate school, be amazed when, you know, these brilliant mathematicians used to make silly mistakes on the board or whatever, and I'm not going to lie, I judged them, and then I became a math teacher. I'm like, it's kind of hard to talk and actually do this at the same time. Anyway, okay, so what this is, if we do this, we get something like 50 and 5/8. That's what I have in my notes, but you should probably check me, okay? So when we look at this, this guy right here, we call this the marginal, I should have said this before. This is the marginal productivity of labor. Productivity, I know that's not right, of labor, close enough. Okay, this makes sense because we know what marginal means. So the derivative with respect to x is the marginal productivity of labor. The derivative with respect to y, of course, is the marginal productivity of capital. Okay? All right, so when I put these numbers in, let's look at this 30 and this 50 and 5/8. So I want to talk about what these mean. So look at this one right here. What this means is, so if I hold my capital at 16 units. Okay, that's not going to change. This 81 here, what that says is if I increase labor, let's just say an increase. If I increase labor by 1 unit, what this 30 represents then, right? This 30 we got, that says that I will increase goods, right? I'll increase production by about 30 times my change. So 30 times 1, which is 30. I hope that makes sense. Here, if I leave, let's look over here and then we'll be done. If I leave my units of labor fixed at 81 and I look at 16, if I increase capital by 1, we're just saying 1 unit because it's easy, right? Then what does this say? This says that I would increase production by 50 and 5/8 times 1, which is 50 and 5/8. So about 50 units of good. So if I had 1 unit to increase, either with labor or capital, what this suggests is that I should put that unit increase into capital, because what will I get? I'll get a larger increase in production. Okay, assuming we want to increase production, which I assume we do. I hope that makes sense. As always, will you please, please, please email me or call me, or I don't know what else you can do to get a hold of me. But I will always help you if you have any questions on this. Kind of nice, we only have 1 section this week. So please let me know if you have any questions. Thanks.